Good morning. Welcome to Talks at Google. We're very fortunate today to have with us Dr. Geoffrey Kerchner to speak with us about the biotechnological assault on Alzheimer's disease. Like for so many of you, this is something very personal to me and to so many others. My mother had 7 children and went through a divorce and finally decided to get her college degree at the age of 40. She got her Bachelor's of Science in Nursing, went on to get her master's degree and then her PhD and taught at the university level. And then, unfortunately, in the course of her teachings, was struck by this disease. And it's something that there's not much we can do about. It's one of the reasons why I joined the board of directors at the Alzheimer's Association and colleagues with Geoffrey on that board. But this is something that we really need to put a lot of effort behind. And Dr. Kerchner is here today to talk to us about what is going on with the therapies associated with this disease. So Dr. Kerchner is a senior medical director at Genentech, an adjunct clinical associate professor of neurology and neurological sciences at Stanford University School of Medicine. He designs and oversees clinical trials of novel therapies for Alzheimer's disease and other neurodegenerative illnesses, while also maintaining an active clinical practice at an academic memory clinic. He is also on the board of directors at the Alzheimer's Association of Northern California and Northern Nevada. He graduated from Harvard College and received his MD and PhD degrees from Washington University in St. Louis. And so please help me welcome Dr. Geoffrey Kerchner.
Great. Thanks very much, Andrew, and thanks to all of you for coming this morning. So one of the things that I have the great pleasure of being able to continue doing, despite my kind of 2 different day jobs, one at Genentech and one at Stanford, is I get to continue to see patients. And one woman whom I saw fairly recently is a 67-year-old woman whose husband died a few years ago. She lives in Palo Alto by herself in the family house. Her daughter has kind of moved on to Manhattan, so lives in New York, talks with her mom frequently by telephone. But her mom's kind of on her own out here. She's gotten used to being alone. She's got her nice, happy life here in Palo Alto. Speaks with her daughter by telephone, complains to her, "Why don't you come visit me more often?" And so in the midst of one of these complaining episodes, her daughter says, "Fine, I'll schedule a visit. Let's come out and see you." And so they planned this wonderful weekend together. So her daughter arrives. I think it was on a Friday evening on a flight from New York. Sees her, greets her mom in the evening when she gets to the house. They have a nice long conversation. Mom tells her about this great farmer's market that's open on a Saturday morning in Palo Alto, where apparently you can get like some nice brunch food. And so they make this plan. Tomorrow morning, we're going to get up early, go to the farmer's market. We're going to have a nice brunch there. Time to go to sleep. Daughter wakes up in the morning fairly early, she feels, looks around the house. Mom is nowhere to be found. She gets a little bit panicked. I mean, she gets out, goes, it looks like the car's gone, actually. Where in the world could her mom have gone? Her mom hasn't sort of joined the cell phone revolution, and so she doesn't have, the daughter doesn't have any way to contact her. A little while later, around 11 o'clock in the morning, finally, daughter's in distress. Where did mom go? 11 o'clock in the morning, her mom pulls up in the driveway, gets out of the car. The daughter comes outside screaming, "Mom, where have you been? We were going to go out to the farmer's market this morning." And her mom turns to her and says, "Oh, honey, when did you arrive?" On the telephone over the past few months, in retrospect, now this is the daughter telling me this story in clinic with her mother sitting next to her. Her mother having, just some, kind of, makes excuses for how this could have happened, and it's not such a big deal in her mother's eyes. But the daughter, in retrospect, kind of looks over the past several months, and yeah, mom's been a little bit forgetful, maybe hasn't been so aware of like what the date is and things like that. Her daughter kind of been brushing it off, but this event really, was different and really stood out in her daughter's mind as being, something that's clearly abnormal. So this is why they came to see me in clinic. Her mom's otherwise pretty functional. She's maintains the household. I mean, she's, eats 3 square meals a day. She goes shopping. She's got her volunteer activities that she participates in. She drives. She hasn't been in any accidents. I mean, she's functioning just fine. One of the challenges that we have as neurologists is when to sort of put the label of a disease on a patient like this. And Alzheimer's disease, which is what we're here to talk about today, we've come to understand kind of spans a very wide spectrum. Alzheimer's disease actually starts in the brain years, decades probably, before the first symptoms hit. And we'll talk a little bit about what those brain changes are. And so there's some kind of dividing line between normal and what I'll call preclinical Alzheimer's disease, which is that stage of the disease where you've got the brain changes, but you don't have any symptoms yet. And I think the field is very uncertain about where this line is between normal and preclinical disease. At some point, you start to get mild symptoms. Maybe a doctor would call a patient, say that a patient has mild cognitive impairment, where maybe their scores on a memory test are now abnormal. In fact, this woman, I subjected her to a memory test, and in fact, she scored abnormally on it. But asking her every question you can think about daily function, and she's just fine. There's nothing that she's missing in terms of daily function. We call that prodromal Alzheimer's disease, when you have, some memory test abnormalities, but you're able to hold it together. And this thing that we call dementia is the very end stage of the disease, and this is where you now need help from outside people in order to get by day to day. You can no longer work. You might need help balancing the checkbook or just maintaining the house. So we regard this as being kind of the end stage of the illness. And you can imagine that there's a lot of people out there who need help with balancing their checkbook and sort of maintaining their calendar and so forth. And there was a day where we sort of thought that when you get old, it's natural that you lose the ability to do these things, but that's not what the medical profession now believes. We don't think that losing the ability to maintain your calendar or your checkbook is part of the normal process of aging. That is an illness. The statistics are pretty striking. So the Alzheimer's Association is folks from our local chapter are here with me today. And they are the leading advocacy group for patients with the disease. And every year they assemble statistics, and these statistics are staggering. These are the latest 2017 numbers. So, more than 5 million Americans, more people die of Alzheimer's disease than of breast cancer and prostate cancer combined. It costs an enormous amount of money when you take into account not just the costs of caring for the patients and housing patients who need all this extra help, but also what about all those unpaid hours of work that spouses and adult children have to put in for taking care of these patients. So this is an enormous illness. In fact, I think that this is the greatest health challenge of our generation. In many ways, we've gotten on top of things like heart disease and cancer. Neither of those is cured, but they're well managed now, and we have a good understanding of what the risks are and how to keep people alive without heart attacks and cancer. But Alzheimer's disease is the one disease that doesn't have any treatment available that can stop or even slow the disease. We really have nothing. So, I attend this clinic and I take care of patients like the one I said, and a lot of what I do is just educating them on what the illness is, but I don't do a lot of treating because we really don't have any effective treatments to offer. So what are the symptoms? So just like this patient, the inability to kind of remember things that just happened, the inability to form new memories is sort of at the core of how this disease starts in most people. And this relates to a structure in the brain called the hippocampus. This is where new memories are formed, and it is the first place in the brain to get the distinctive changes of Alzheimer's disease that I'll tell you about in a moment. These brain changes do spread to affect other parts of the brain, and so therefore other cognitive functions like language function, visual spatial function, and executive function, all of these different so-called cognitive domains end up getting affected as the disease progresses over time. Now, I do in my clinic get confronted with patients who come to me and say, for 30 years, doctor, I've not been able to remember the names of people. That's not a disease. I have trouble remembering people's names too. So there's a lot of people who are, worried about, what they perceive in themselves to be cognitive weaknesses. That doesn't necessarily constitute an illness. What gets my attention is when somebody tells me about symptoms that have changed over time, especially over the past year or two. That's what gets my attention. So what is Alzheimer's disease? It's actually defined by what your brain looks like in the microscope after death. So there's these characteristic changes of plaques and tangles. These plaques are made up of a protein that we came to discover is called the beta amyloid protein. So these plaques are in the gray matter. It's in that exterior mantle around the outside of the brain, kind of sitting there between neurons. It's these spheres of an aggregated protein. And there's a bunch of cells, inflammatory cells kind of surrounding it, but it's made up mainly just of this one protein. Separately, kind of surrounding these plaques and also in other areas of the brain that don't have plaques, there are these other structures called tangles. Tangles are an accumulation of a completely different protein called the tau protein. And it aggregates inside of neurons, whereas plaques are outside of neurons. So how these proteins come to be aggregated and what exactly the aggregation of these proteins has to do with cell death is still a bit of a mystery. But it's been about 100 years, 111 years to be exact, that we've understood that this is what the brain looks like in the patient, in a patient with Alzheimer's disease. It was in 1906 that Alois Alzheimer, who's a German pathologist, finally at a conference presented the findings from a patient, August Dieter, that he'd been basically obsessed with for a number of years. He met this patient in an insane asylum in Frankfurt. She had a number of strange symptoms, including memory loss, that fascinated him. She was only 51 years old. She actually had a rare kind of Alzheimer's disease that you get as genetically. So she directly inherited a gene for this disease from one of her parents. This is an uncommon way to get Alzheimer's disease, but it is a way to get Alzheimer's disease at age 51. So he became obsessed with this patient, found a way to basically be her pathologist at death, and it's kind of macabre, but he was sort of waiting for this woman to die because he couldn't wait to look at her brain. And this is what he found. He was the first one to describe these plaques and tangles. So at this psychiatric conference in 1906, he presented this paper. He was largely ignored at the time. The story is that the talk that came right after him was on compulsive masturbation, and everybody in the audience was there to witness that next talk, and they were eager for Alzheimer to get off the stage so that that next speaker could come on. So his findings were, largely ignored for quite a number of years, and for most of the 20th century, we thought that Alzheimer's disease was a rare disease of young people. And it's because nobody did autopsies on grandma, all right? We always thought that old people have memory loss and that's just a normal part of aging. But it was in the 60s and 70s, kind of, after the war, that people started doing more autopsies and kind of came to this realization that instead of being a rare disease of young people, it's actually an extremely common disease of old people. And it was in 1985, as kind of the interest in Alzheimer's disease in the scientific community was starting to rise, that finally somebody discovered that the protein that was in these plaques, because these plaques were just spots on the brain and nobody knew kind of what they were made up of. This was when this A beta protein was, this amyloid protein was discovered as the main ingredient in these amyloid plaques. And after this, so this was a seminal discovery in 1985. And following that, there was an explosion in the scientific literature. This was at a time when we were starting to do protein biochemistry and cell biology and kind of the tools that, that biologists use to characterize proteins and pathways and so forth were now blossoming. And so this whole understanding of what the A beta protein is kind of came to light in the late 80s and early 90s. We understood that this A beta protein was actually a subcomponent of a larger protein that came to be called amyloid precursor protein, not a very creative name. And we came to understand that some cleavage events, so that amyloid precursor protein gets cut at two different places in order to liberate this short string of amino acids that is the A beta peptide. And that for probably reasons that are just kind of random and having to do with the biochemical nature of this little A beta peptide, it tends to be a little oily, it tends to stick to itself, it tends to just glum up in these big globs that you see here. The plaques are actually when hundreds of thousands or millions of these molecules of A beta all get glummed together in this really dense insoluble blob that the brain just doesn't know what to do with. And the discovery of all these pathways ended up leading to the postulation of the amyloid hypothesis, which is this statement, that beta amyloid accumulation is the primary cause of Alzheimer's disease. And this was revolutionary in the field. And what was the evidence behind this? Well, first, you could so now in the laboratory, people took this A beta protein, dumped it onto cultured cells, or squirted it into the brain of mice, and in fact, it could induce neurotoxicity, so this protein could kill neurons. All right, so that makes sense. That's supportive evidence that amyloid is bad for you. Probably most compelling was genetic evidence of the importance of A beta. So remember I told you that patient from 1906 that Alzheimer had examined, she had a familial form of the disease. So it turns out that she had a point mutation, just a single element of her DNA was changed in a protein that mediates one of those cleavage events in the amyloid precursor protein to liberate A beta. It makes that enzyme work too much. So basically it leads to an overproduction of the A beta protein. Another piece of genetic evidence, we came to discover that individuals with Down syndrome, what is that? That's trisomy 21. That's where you accidentally get 3 copies of chromosome 21 instead of the usual 2 copies. Guess where the amyloid precursor protein gene lives? It lives on chromosome 21. And it turns out that individuals with Down syndrome, if they manage to live to the age of 40 or so and don't die of heart disease or of other complications of their genetic syndrome, they will have a 100% chance of getting Alzheimer's disease. All right, so their brain shows the exact same changes as the patient that Alzheimer took care of, and the same changes that that all of our older demented patients have. So this genetic evidence is really compelling. So just single genetic changes that lead to an overproduction of this one protein are sufficient to cause Alzheimer's disease. And so scientists really got excited about this amyloid hypothesis, and now we think we're on a pathway towards curing the disease because now we have the causative protein in the brain, right? Evidence came, we sort of assembled this picture of how Alzheimer's disease starts. That the amyloid hypothesis postulates that A beta is front and center, that accumulation of amyloid beta starts when we're healthy and probably reaches a near maximal level by the time patients like this 67-year-old woman that I told you about comes to my clinic. Probably the level of A beta in her brain was more or less maximal at that time point. And it persists, through the prodromal and dementia stages of the disease. Downstream of that is the accumulation of that tau protein. Remember I told you about the tangles that you see in the brain. And eventually that leads to neurodegeneration, and symptoms are the last thing that happen. Couple important things to notice from this graph. One is sort of the optimistic view of this graph is look how resilient the brain is. It can withstand a lot of amyloid plaques and a lot of tau tangles before a patient exhibits the first symptom. Okay, so symptoms are long delayed in time from the accumulation of the damage in the brain. The downside of this is that by the time a patient shows up in my clinic, the brain sort of looks like a war zone. This might make it a little bit complicated to start treating the disease at the point that somebody has symptoms. So bear that in mind. So again, amyloid hypothesis, here we are now in the 1990s, and everybody in the scientific field is super excited about the amyloid hypothesis, and now drug companies, now we're getting to the biotechnology part of the talk. Drug companies are starting to glom onto this and say, hey, we've got a gold mine here. We need to develop drugs against this amyloid protein. It turns out that it's not so easy to create the kind of drugs that you put into a pill, right? Small molecules that you can take as a pill and somehow do something to this amyloid protein to neutralize it. That turns out to be not so straightforward. But scientists like Dale Schenk had this idea, if the problem is a protein, we have this whole apparatus in our body to deal with bad proteins. It's called the immune system. What the immune system does is it recognizes bad proteins, for instance, proteins that come from bacteria or viruses, a protein that's recognized as being foreign. And the immune system goes crazy when it's confronted with a foreign protein, and it has all these, advanced mechanisms to try to attack that foreign protein and to get rid of it in the most efficient manner possible. So Dale Schenk and others had the idea, why don't we hijack the immune system, train the immune system to think that A beta is a foreign protein, and we'll just let the immune system do the hard work of finding all that A beta protein in the brain and get rid of it. And so, what he was able to achieve in mice, scientists now in the mid-90s had created mouse models of Alzheimer's disease based on these human genetic cases. So you introduce in mice those same genetic mutations that humans who have familial forms of Alzheimer's disease have, and lo and behold, these mice develop amyloid plaques in their brain, and they get demented. And so what if you administer a vaccine to these mice? So a vaccine is a way of introducing a protein, kind of showing it off to the immune system with flags saying, foreign, bad, attack. By giving a vaccine with this A beta protein to mice, he was able to absolutely clear these amyloid plaques away. It was beautiful. These mice, not only did their brains look normal, but they also behaved normally. They did not get demented. And so this was in 1999. This paper was published in Nature. Several biotechnology companies were already all over this. They had amyloid vaccines ready to give to humans. And so that was actually being done in parallel. So the first vaccines were given to a group of humans. The field was extremely excited and absolutely sure that this was going to be the cure for Alzheimer's disease, that this vaccine would do in humans exactly what it did in mice. Do you know what happened? Unfortunately, about 6% of the people in these clinical trials got meningitis. Now, how did that happen? In retrospect, it shouldn't have been so much of a surprise because it turns out that patients with Alzheimer's disease have, such an abundance of this amyloid protein in their brain. I mean, literally milligrams of it if you could purify it out of one human brain. There's so much of it there that if suddenly the immune system goes berserk, over a protein that's in super high abundance within the brain, not surprisingly, you set off a pretty bad immune reaction. And you can imagine that having a lot of inflammation, a lot of immune cells going berserk around stuff that they think is foreign around the brain can cause problems. So they had to stop this clinical trial early because of safety. It was not safe to give people a vaccine. The problem with a vaccine is that, once your immune system is trained, you can't turn off the immune system, aside from giving people strong chemotherapeutics or something. You can't really stop the immune system from all this crazy attack of A-beta. So this was pretty disappointing. We followed these patients actually to death because we were so curious about, did the vaccine at least do something positive? Unfortunately, all of these patients, their dementia continued to worsen over time. And there wasn't, the patients who received placebo or patients who got the active vaccine, there wasn't really any difference in how their Alzheimer's disease progressed over time. A number of them ended up passing away, and autopsies were done in the context of this research. One interesting thing they found, you probably have a sense that when you get a vaccine, sometimes it takes and sometimes it doesn't, or sometimes it takes a little bit. In other words, your immune reaction against a vaccine, it can vary, and you can actually measure this. You can measure the titer of an antibody response. And so that's what they did in these patients. They looked at some patients who had no antibody titer against A-beta, people who had sort of an intermediate antibody titer, and patients who had high antibody titers against A-beta. And they saw that there was actually a really tight association between that finding and the degree of amyloid plaques that they found in the brain at autopsy. In other words, patients in whom the vaccine really took well had hardly any amyloid plaques to speak of, whereas patients who were either treated with placebo or in whom the vaccine didn't really take, they didn't have much of a titer against A-beta, they had a lot of plaques left. So this suggested to the field that the vaccine did what it was supposed to do. It presumably helped to clear amyloid plaques out of the brain. But it was a little bit frustrating that it didn't seem to have any effect on the clinical course of the disease. So vaccines aren't safe because, as I said, you can't turn off the immune system once it starts. But what you can do, and here's where companies like Genentech and others, really come to the fore as being important. What you can do is to manufacture an antibody. All right, so when you give a vaccine, you're relying on the body to generate its own antibodies against this foreign protein. But you can bypass that and instead engineer your own antibody, and we call that a monoclonal antibody when it's a single antibody that's manufactured in great abundance in a manufacturing facility like Genentech or AbbVie or one of these big companies has. So you can engineer antibodies that attack A-beta, and the nice thing about this, you put this inside of an IV bag and you administer it to a patient. If a patient has a side effect, well, you can simply stop administering the antibody, right? So now you have control over the immune response. You can shut it off if you need to. And so this was exciting, and now the field is excited again. We now have the cure for Alzheimer's disease. We're sure of it. Bapineuzumab was the first drug of this next generation, the first of these monoclonal antibodies that was tested in big clinical trials. Everybody was very excited about it. No fewer than 4 major pharma companies were involved with this. Wyeth and Elan kind of entered a partnership. Running these big Alzheimer's disease studies are very expensive. So it started off as a partnership between Elan and Wyeth. I think Johnson & Johnson then got a stake in one of those companies, and then Pfizer bought Wyeth. Anyway, 4 different companies all had a hand in this. Everybody was sure that this was going to be a cure for Alzheimer's disease. Unfortunately, the results of 2 big, massive international phase 3 clinical trials revealed that there was absolutely no effect of this drug either on memory function or functional abilities of these patients. In addition, there were side effects. Remember that meningitis that happened with the vaccine? So we saw brain swelling in patients who were given, in some of the patients who were given this antibody, and probably it was part of the same thing as that, the quote unquote meningitis cases that happened with the vaccine. This is just brain inflammation. Okay, so what we told ourselves in the field at the time was the reason that this clinical trial was negative was because we couldn't get the dose high enough without getting this side effect. Okay, we couldn't get the dose high enough to really clear enough plaques out of people's brains in order to have that beneficial effect. So we convinced ourselves that, this approach is not dead. All right, it's just that this side effect ended up being limiting. So surely there must be some way around. Roughly at the same time, Eli Lilly had this antibody called Solanezumab. So what they tried to do here, they engineered their antibody so that it bound to a form of A-beta that was less likely to kind of cause this big inflammatory reaction. So they really attempted to dial down that side effect so that they could hopefully maximize the therapeutic effect of the antibody. Okay, the field is excited again. And in fact, there were no side effects of this antibody. It was safe. This is great. You can administer now antibodies against A-beta in a way that's safe, that doesn't cause this brain swelling. But unfortunately, their two big international phase 3 clinical trials, well-run trials, were negative. No effect on memory, no effect on daily function. There was a little shred of optimism, though. Now, who were the people that they enrolled in their trial? It's actually the same kinds of people enrolled in the Bapineuzumab trial. These were patients who already had dementia. They were worse than that woman that I told you about at the beginning. These were people who could no longer live alone, people who needed help with daily function. And remember how I told you that's actually at a fairly advanced stage of the illness? When they looked at the subgroup of patients in their clinical trials who were at the mildest stages at the start of the trial, right? Because there's a bit of a spectrum of patients who are enrolled at the beginning. They're not all the same. When they sliced the data and looked at the most mildly affected patients at the beginning, they saw a benefit of the drug, about a 30% improvement in those patients. This was enough evidence for them to run a brand new phase 3 clinical trial. And they came to an agreement with the FDA that they just would need one more trial, now conducted just in those mild patients. And it read out about a year ago. It was positive, but the effect was so modest, something like a 5 to at most a 15% improvement. It wasn't enough to move forward because these therapies require monthly IV injections, $150,000 to $200,000 per year that your insurance company gets charged, a 5 to 15% benefit. It's not enough. It's not enough. And so they ended up deciding not to move forward with that drug. At the time that Bapineuzumab and Solanezumab were running those first generation clinical trials, another big discovery came about in the field. We used to have to wait till autopsy to know, to be able to look at the brain to know whether a patient has amyloid plaques or not. But this great technology came into widespread use, the use of an amyloid PET tracer. So this is a technology where you can use a small molecule that binds with high affinity to amyloid plaques, and you radiolabel it. All right, so you inject patients with this radioactive tracer molecule that in a healthy person finds nothing in the brain to bind to, and it goes to your bladder and you pee it out and it's gone. Or in a patient with Alzheimer's disease, it finds something to bind to in the brain and it sticks around. Right, so you inject a patient with this, wait 60 minutes, put them in a positron emission tomography scanner that detects radioactive emissions to ask the question, did this tracer find anything in the brain to bind to? And so you can see some examples of pictures of patients with Alzheimer's disease compared to healthy controls. One big discovery was that the patients who were enrolled in these initial clinical trials, in whom expert doctors like me had the opinion that this patient looks to me like a typical clinical case of Alzheimer's disease, about 80% of the time, expert clinicians like me are right. And about 20% of the time, patients don't have any amyloid in the brain. They don't have Alzheimer's disease. They have some other illness that's making them demented, but it's not Alzheimer's disease. Well, this is a problem if you're running a clinical trial and 20% of the people enrolled in your trial don't even have the disease of interest. So this was one big lesson learned. And maybe this was the reason why some of these early clinical trials failed. Aducanumab was the next big monoclonal antibody. This is made by a company named Biogen, a little company up in Cambridge, Massachusetts. They tried to solve these sins of the past. So they designed their clinical trial. They required people to have amyloid PET imaging in order to get into the trial. So they had to demonstrate positive evidence that they actually had amyloid in their brain. In other words, that they truly had Alzheimer's disease. It turns out that their antibody does bind to the form of A beta that might cause those inflammatory reactions. But they decided as a company that they were willing to tolerate that if they could somehow see some efficacy. And they really tried hard with the dose, because another reason why that Lilly antibody, Solanezumab, might have failed, they used a fairly low dose of it. And it turns out that it's really hard to get antibodies that you inject intravenously to cross the blood-brain barrier to get into the brain. There's something like a 10,000-fold barrier, concentration gradient between the blood and the brain. And so you have to really administer a boatload of these monoclonal antibodies in order to hope that enough of it crosses and gets into the brain. So another reason why Solanezumab might have failed is that their dose might have been too low. So Biogen tried to correct these sins of the past. They enrolled patients who definitely had Alzheimer's disease, and they really tried hard to push the dose up as high as they could. And now, for the first time ever, this was in 2015 at a big international conference where we saw these data for the first time. These data show that increasing doses of the drug, both at 26 weeks, so about 6 months, and at 54 weeks, so about 1 year, produce reductions in how much amyloid is in the brain measured by that amyloid PET imaging, right? So you put people into the scanner at baseline to make sure they have amyloid in the brain, but then you put them back in the scanner at 26 weeks and at 54 weeks, and you see actual reductions in how much amyloid is in the brain. So their antibody is working, at least biochemically, to remove plaques. This was incredible. Nobody had ever shown this before in the field. Did it help people clinically? And the answer was here, again, for the very first time ever, yes, there was evidence of a clinical improvement. So this CDR thing, this clinical dementia rating scale, is kind of a summary of patient symptoms. And they were able to demonstrate not so much at 26 weeks, but at 54 weeks, there was a nice reduction in how much people worsened on the symptom scale. Now, this was a small trial. There were, just small, you can see the N size, 31 in the placebo group, 23, 27, and so forth in the various treatment arms. This is way too small to get FDA approval for a medicine. You need to run a trial with hundreds of patients to really demonstrate that this effect is reproducible. So this was a small trial, but it was the first time anybody had shown an effect like this. So a couple of big international phase 3 clinical trials are going on right now with this antibody. It does cause that brain swelling that I showed you, and a number of people actually dropped out of this trial because they got that brain swelling and had to quit. They got sick from it. And so the field is really waiting to see how to balance the side effect versus any positive benefit you get with this drug. And so this is one thing to watch for. In a couple of years' time, we're going to see this clinical trial read out, and it could be revolutionary. In the meantime, people have developed drugs that target these enzymes that produce A beta in the first place. So there's this gamma secretase enzyme that makes one of those two cleavage events that creates the A beta protein. Turns out that inhibitors of gamma secretase are poisonous, makes people sick. Okay, that doesn't work. Beta secretase is the other enzyme that makes the second cut that liberates that A beta protein. This inhibitors of beta secretase seem to be less poisonous. Now a number of companies have beta secretase inhibitors that are in clinical trials. And just last week, there was a big conference in Boston, Clinical Trials in Alzheimer's Disease. And we saw for the first time publicly disclosed data from Merck, who had one of the first of these beta secretase inhibitors. And then fortunately they reported negative data in patients with mild to moderate Alzheimer's disease. And they were able to show that in fact their inhibitor did seem to reduce the amount of amyloid plaques in the brain. So again, there's this disconnect between evidence that the drug was doing something good biochemically, but it wasn't able to produce any benefits for the patients. And so we're all wringing our hands and wondering, is the amyloid hypothesis dead? Aducanumab, that Biogen antibody, looks promising, but it was a small trial, and we've been in this field long enough to have seen, small trials that look really promising that just vanish when you bring it to a big international phase 3 trial. We've been in the field long enough not to get too excited. And given the number of failures of drugs that target beta amyloid, a number of us are wondering, is the amyloid hypothesis dead? Tau is, this protein that, again, it makes tangles, the other main pathological hallmark of Alzheimer's disease. It seems to be downstream of beta amyloid. And one attractive thing about, by the way, the Taoists and the Baptists have been fighting ever since the 1980s, ever since these proteins were discovered, and the Baptists have had the upper hand for a long, long time. But this decade has really been the decade of the Taoists because of all these negative results that have come from beta amyloid trials. Tau does have some attractive features. First of all, it seems to build up in the brain not decades before somebody gets symptoms, but at the same time that somebody has symptoms. So this is attractive. If there's a nice temporal correlation between the buildup of a pathology and the symptoms that somebody has, this says that there must be some kind of better proximity of tau to the neurodegenerative process. And furthermore, there's this nice correlation in space. So the exact same brain cells that show evidence of tau pathology are the same ones that are producing symptoms. So we know a lot about different regions of the brain and what kinds of cognitive things different parts of the brain subserve. So patients with language problems will have problems in their left hemisphere where the parietal and temporal lobes of the brain join. And in fact, those patients who have language problems in fact show tau pathology right there, right where you'd expected. Not true of amyloid. Amyloid does not show up in the right places in the brain. So tau has this nice tight relationship in time and in space to symptoms. Therefore, it seems to be more proximate to the symptoms our patients have, and this is part of what makes it an attractive target. And so now we and a number of other companies have drugs, now again, monoclonal antibodies targeting tau, and it's going to take some years for these clinical trials to read out. So what we've learned, it's a number of things. We've learned that you need to not be shy about dose. You need to make sure that you enroll patients who are early enough in their disease where full-scale neural destruction hasn't set in yet. You need to make sure that you actually enroll patients in trials who actually have Alzheimer's disease. And so using these molecular biomarkers to characterize patients at the beginning of a clinical trial is important. Things to watch for: this BACE inhibitor, this beta secretase inhibitor called varabesistat. This is from Merck. This is the one that showed a failure in patients who were already demented. They have another clinical trial that's still ongoing in patients with prodromal Alzheimer's disease, so a milder form of the disease. And so even though we're now fairly pessimistic about this mechanism, we'll see that trial read out fairly soon. After that, we'll see these big phase 3 trials of aducanumab read out. That was the one that looked promising in the small phase 1 study. And then there's a couple of other antibodies, crenezumab and gantenerumab, that are testing slightly different mechanisms against A beta. And then it's going to be a few more years in the future where we'll see these tau trials read out. So hopefully this has been helpful. You'll see, I mean, many of these trials actually reach the headlines in the New York Times when they read out as negative. And so you'll see announcements of these trial results as they come in the coming months and years. And hopefully now you have a little bit of a perspective on kind of the story behind where these treatments came from. So I'll pause now. I think there's 5 minutes left and take some questions.
I have a couple questions, but I guess I'll cycle around. So the first question I had was that these proteins, the tau and the AB, must have some kind of function in the body. So I'm wondering, first of all, why they exist in the first place in the body, what function they fulfill, and then potentially by attacking these proteins, what sort of side effects are there eliminating them from the body?
That's a great question. Despite, now many decades of research on the amyloid precursor protein and the A beta peptide that, is liberated from it, we still don't know what the heck it does. You can knock it out in mice, doesn't have much of an effect. We haven't, other than brain inflammation, we haven't seen other side effects of drugs that seem to, that aim to get rid of A beta. Tau is a protein. Its normal function is to kind of sit on microtubules. Microtubules are part of the skeleton of a neuron that in the axons, the long protrusions, the wires from neurons. These microtubules are sort of the backbone of axons. Tau is this protein that kind of sits on top of that. There are other proteins that also sit on top of it to kind of stabilize these microtubules. Tau doesn't seem to be unique. If it's gone, other proteins do its job. You can knock tau out of mice, and the mice have absolutely no phenotype. There's no symptoms. They're normal. Tau probably, I think we understand a little bit about what tau does normally, but it's a redundant function to other proteins. The amyloid protein, we really, again, after decades of research, really don't understand what it does normally, if anything.
Hi, thanks very much. I had just two quick questions. I was wondering if you can comment on the relationship between cardiovascular disease and Alzheimer's, and also the role of diet in specifically like turmeric, this impacts on Alzheimer's.
Great. So risk factors for Alzheimer's disease include cardiovascular disease and diabetes, the metabolic syndrome that's become so endemic in our society. The relationship is a little bit unclear, and it might be indirect. Remember, these pathological changes in Alzheimer's disease build up over decades. And there's a threshold effect, right? There's some threshold at which those biochemical changes in the brain become severe enough that now you have symptoms. A number of factors determine where that threshold is. Other damage to the brain, for instance, to the brain's vasculature, might lower the threshold so that a given amount of A beta and tau that in one person doesn't cause symptoms, in somebody who has simultaneous damage to the brain, chronic damage to the brain from poor blood supply because of high cholesterol and high blood pressure and diabetes, maybe that threshold is lowered. So it could be an effect like that. Some scientists think that there might be a more direct effect on beta amyloid metabolism, but I think that's less clear. Things like diet and exercise probably feed into it. Also, education level. How much, attending lectures like this in the middle of the day is good for the brain. You form extra synapses and make it possible for the brain to sort of weather damage a little bit better. So there's a number of complex things that feed into that threshold effect. But those things may not affect the actual accumulation of the amyloid and tau proteins themselves.
So you mentioned the treatment that was successful for rats but not for people. Was that the manufactured antibody or was it the immunization?
Everything that I've told you about today has cured Alzheimer's
wow.
disease. We have cured Alzheimer's disease over and over and over again. What this tells us is that the mouse models are not great replicants of the human disease.
Got it. Okay, because I was going to ask you if any research has gone into what it might be different about human brains than mouse brains. That is it like our defense mechanisms of our brains that prevent that treatment from working on us?
It's a lot of things. I mean, the complexity of the organ is much greater. The genetics is obviously different. And just the chronicity of the disease. I mean, a mouse only lives 2 years. The human brain, assembles damage from, 6, 7, 8 decades. And it's hard to model that in a mouse.
My mother was prescribed Namendra by her general practitioner, which I know was not mentioned. Is that likely to do anything useful in cases like this?
Good. So there's 4 drugs that are FDA approved for Alzheimer's disease. Namenda is one of them. They're not ineffective. These 4 drugs do something. They squeeze a little bit more juice out of the brain. They're what we call symptomatic drugs, in that they don't change the inevitable course of the disease to worsen over time. They don't change the slope of the curve, but they sort of shift the curve up a little bit. If your mother were to run out of her prescription and stop the drug, she would drop right back down to the curve that she would have been on had she'd never taken it. So these drugs don't fundamentally change anything about the biochemistry in the brain or sort of, the disease process itself. And that's why we call them symptom treaters. The drugs, the drugs are still good because they do something. It's not enough, though. We need so-called disease-modifying therapies that actually interfere in the biochemical progression of the disease in the brain, and actually, change the slope of the curve fundamentally. And that's what these drugs purport to be able to do, although none has been successful yet.
So looking at the graph with the amyloid and the tau, it's like seemed pretty immediately clear that the tau correlates with the symptoms, as you mentioned. First of all, why wasn't that examined sooner? And why weren't anti-tau drugs developed in tandem with the anti-amyloid ones? Second of all, in the mice, you said they squirted the brain with the amyloid protein. Had they done the same thing with the tau and seen if it's the combination of those 2 proteins, or is it one or the other that's actually causing the symptoms?
So it turns out you can present tau to the brain in a way that it's toxic also. But you just ask a question that's at the heart of what has been a big debate in our field for a long time. Why did the Baptists have the upper hand for so many years? Part of it is the genetic evidence. So mutations in tau, they actually cause dementia, but they don't cause Alzheimer's disease. They cause a different disease called frontotemporal dementia that causes degeneration of very different parts of the brain, very different symptoms. It's a different disease to Alzheimer's disease. It's only mutations in that amyloid precursor protein or in the proteins that metabolize it to create the A beta protein, or Down syndrome where you have 3 copies of that gene. It's only those diseases that seem to cause Alzheimer's disease. There's actually in Iceland, there's a family that has a mutation in their amyloid precursor protein such that it cannot be cleaved by one of those 2 cleaving enzymes, and they can't. In that family, you cannot make the A beta protein, and those patients cannot get Alzheimer's disease. So there's this great wealth of genetic evidence, overwhelming genetic evidence of the primacy of A beta as a causative factor in AD, and that's part of how the Baptists had this upper hand for so long, despite that nice temporal relationship between tau pathology and symptoms. Tau was just regarded as being this downstream factor, but not really the root of the disease. That may still be true, but as long as we're treating symptomatic patients, tau might be a better target.
Right, and it seems like you could kill 2 birds with 1 stone potentially and treat the other disease, right? I mean, I
Yep.
guess, does the amyloid cause the symptoms, or is it contributing to the production of tau, which causes the symptoms? Is there an answer for that yet?
Nope.
Ah.
Great. Thanks, everybody.